In our last lesson, we saw atoms form covalent bonds by sharing a pair of electrons. But sharing does not always mean a perfectly even 50-50 split. This diagram shows two identical atoms. They pull on shared electrons with equal strength, leaving them perfectly in the middle. When atoms are different, one pulls harder. We call that pulling strength electronegativity. The stronger atom drags the shared pair closer to its own center. Because those electrons are spending most of their time closer to one side of the bond, the whole relationship becomes uneven. The molecule actually develops distinct sides. This diagram shows what that uneven sharing creates. Electrons carry a negative charge, so the side of the bond that hogs the electrons takes on a slightly negative charge. The side that got abandoned is left slightly positive. We call this a polar bond. Think of it exactly like a physical magnet on your refrigerator, with a distinct north and south pole. Notice that the electron is only being pulled to one side. It hasn't been completely stolen away like it would be in an ionic bond. It's still being shared, just poorly. This diagram of a wooden ruler helps show how these bonds relate. Covalent sharing and ionic stealing are not completely separate categories. They are just opposite ends of a single continuous scale. Most bonds in nature fall somewhere in the middle. Knowing where a bond lands on this ruler helps us predict how a substance will behave. It's our first clue in understanding why some things mix easily and others refuse to touch. Let's look at how this plays out with the most important molecule on Earth, water, made of one oxygen and two hydrogen atoms. This diagram shows an oxygen atom flanked by two hydrogens. Oxygen is vastly stronger, aggressively pulling shared electrons inward. If water were a straight line, these inward pulls would be exactly opposite. They'd perfectly cancel out, leaving no magnetic poles. That straight line cancellation happens exactly in carbon dioxide. Its internal polar poles perfectly erase each other. But water is not a straight line. It's locked into a strict V shape, so its poles no longer point in opposite directions. Because both hydrogens are on the same side, their poles combine, pointing toward the oxygen at the top. As a result, the oxygen side becomes negative, and the two hydrogen points become positive. Having polar bonds inside a molecule is only half the story. The physical shape of the molecule dictates whether those inner bonds turn the whole structure into a working magnet. Watch this kitchen glass. No matter how hard you stir oil and water together, they stubbornly separate right back into two crisp layers. This happens entirely because of their polarities. There is a consistent pattern in how substances interact. Molecules usually prefer to hang out with others that share their same magnetic personality. Polar molecules stick to other polar ones, while nonpolar molecules stick with their own kind. Oil is nonpolar. It has no magnetic sides. Because of this, the highly polar water molecules completely ignore the oil. They prefer to magnetically stick to each other, and they physically squeeze the oil out of the way to do it. Now look at this diagram showing what happens when you drop a salt crystal into water. Salt is made of positive and negative ions. The negative oxygen ends of the water grab the positive sodium ions, and the positive hydrogen ends grab the negative chlorine ions, easily ripping the salt apart piece by piece. When a substance dissolves, it doesn't vanish. It is just going through a very precise process of magnetic matchmaking. Which brings us to a practical problem at your kitchen sink. If water rigidly refuses to touch nonpolar grease, how on earth does soapy water manage to wash a dirty frying pan? This diagram reveals the mechanical secret of soap. It acts as a chemical diplomat. A single molecule of soap has two different sides, a round polar head that loves water, and a long nonpolar tail that loves grease. When you scrub a pan, those long nonpolar tails stab deep into the grease droplet, anchoring themselves firmly inside. With the tails buried, those polar water-loving heads are left completely coating the outside of the grease. They create a protective, water-friendly shell. Now, the polar water flowing from your tap has something magnetic to grab onto. It bonds with the polar soap heads, dragging the entire wrapped package of grease right down the drain. Every time you wash a plate, you are using electronegativity to move grease that water alone could never touch. You are manually commanding subatomic forces right in the palm of your hand. Next time, in our final class together, we'll take all of these invisible rules and see how they combine to build the wider physical world around us. See you then!